But let's go ahead and get started with our next kind of major topic this semester. And it's a pretty important one. Now, there's some content in these slides that I don't think we'll necessarily need to cover because it's a little bit more about applications of arrays that we could actually spend several weeks and treat it like a linear algebra course. But to make sure we have a decent understanding of, at the very least, static allocation of arrays and how we use them in C. And that is some pretty critical stuff. So basic concepts, usage, then hopefully on Friday, but if not Friday, on Monday, strings is just really a special type of arrays with special functions associated with them. And then to some extent, we'll get to some of like engineering applications, but I don't think we can spend as much time as ideally what I would like to spend. There is a direct connection between this topic and a forthcoming topic on pointers, which some people say that's the hardest part of C, and I think we're going to have the right foundation. We're going to be fine for it. I'm trying to keep the two topics separate for now. They are very closely related, but I'm just trying to segment it off. We're going to talk about arrays first, with hopefully not talking about pointers at all. And then when we talk about pointers, it's going to directly connect to our existing understanding of arrays. Lab 5 is a bit of a challenge. Hopefully you're going to enjoy what you're working on with that one as well. I know some of you have already gotten started. So I've used the term already. We've used in a couple small circumstances. We've used them already just to more formally introduce the concept. An array. It's a collection of two or more memory cells that are associated with a single variable name. So syntactically, when you want to declare a variable as an array variable, it looks very similar to what we were already doing for what we're now going to call and refer to as scalar variables, where there's just a single value we're storing. We declare first the type, then the name of the variable that's going to be associated with an array, and then in the square brackets, how many locations, how many variables, or how many things we are storing associated with that variable that we have defined. So double x, and how we actually would say this out loud, double x of 8, or double x of size 8, or an array x of size 8 of type double, however you want to phrase that. That's defining an array variable that we're calling x, and it's going to correspond to 8 different values of type double. If we just need a single value x, we just say double x. If we want in our program to have 8 doubles at a given time associated with a variable name, we use this concept of arrays with that array syntax. Then when it comes time to actually use that variable, we generally have to so-called subscript the array. Using effectively the same syntax, although it's now used in a slightly different purpose here. Here we use the square brackets at declaration time to say, give me 8 of those doubles. And then when it comes time to use it, we still use our double or our int or our float or unsigned short, all the different variable types we have. We still use them in exactly the same ways we've been doing it already with our existing variable types. We just need to make sure that by and large, we're grabbing a single value from that array at any given point in time. That's what it means to subscript the array. We are saying we're going to take an individual value from that array, and then that's going to be the double or the int or what have you that we're interested in that point in time. So it's the same syntax, but it's doing two slightly different things. When we declare it, that says, give me memory allocation, give me enough space, and give me a variable name called x that's going to store 8 of those doubles. That's what that 8 means in this context. Whereas now when we're actually using it, so y equals x of 3, or y equals x of 3 plus x of 4. That x of 3 is subscripting the array. It's saying, of these 8, give me offset number 3 into that array of 8. And if you know that, then you're good to go. That's all you need to know about arrays. That's it, essentially. Where it starts to get a little bit tricky, and as I already said, arrays and pointers are very closely coupled concepts, and in a couple weeks we'll get to it. Until we learn how to write code that allows us to do what's referred to as dynamic memory allocation. It's a fancy sounding term that literally just means as our program is running, we have variables that determine how much memory we need for an array or for some other variables that we have in our program. We will learn how to do that. Until we learn how to do that properly, our assumption for this course, W285, week 6 of the semester, is that we're going to have so-called statically allocated arrays in our programs that we write. Meaning, we're going to be defining these arrays, and they're going to be of this type, double x of 8, where 8 is static. 8 is known at compile time. The compiler can look at your code and say, hey, you put an 8 there. I understand what 8 means. 8 means you need 8 of these. That is not a limitation of C as a programming language. It's just a limitation that I am sort of imposing this week, next week, this semester, to kind of limit the number of challenges we would face with working with arrays in our programs. One quasi workaround for now would be to do something like this in your code. That if you want to have code that still has some flexibility in terms of the size of the arrays that you're declaring and using in your program, but we are not yet wanting to deal with all the extra conceptual overhead of dynamically allocating the arrays, you can still use this concept of static allocation, but instead of hard coding the value directly as being, in this example, 5, you could instead use this compiler macro, right? This preprocessor macro where you just define this token is always going to correspond to a value of 5. We've seen these preprocessor macros before. It literally tells the compiler, every time you compile this program and you see this sequence of bytes, this keyword, replace it with the number 5. So it doesn't really change the fact that it's statically allocated. It's still as if we defined it with length 5, but it gives us a little bit more flexibility with how we write our program, that if I decided that later I started off with length of 5, but I actually wanted length of 15, then if I wrote my program accordingly and was careful with how I was using this value in my program, in theory at least, I want to go from 5 to 15, update all my loops and whatnot, I would just need to change this, and then the rest of the program would still work. It's still static. I would then need to recompile the program to get that array of length 15 versus that array of length 5, but it gives it a little bit more kind of programmer dynamic nature than what we have if everything is directly hard-coded in there. When we declare the array, we can choose to initialize it at declaration time, just like we can choose to initialize our scalar variables as well, with some different syntactical allowances. We can declare int my array of length. We use curly braces for whatever reason. We initialize all the elements in that array with the appropriate number of things we want to initialize it with. In fact, although there's benefits and drawbacks either way, if we do use that declaration initialization of our array, that syntax where when we declare the variable of an array type and we also are initializing it, we actually don't even need to specify the size. The compiler is smart enough to determine I'm declaring an array, it still has the square brackets there, and I'm initializing it to 1, 2, 3, 4, 5. The programmer's intention, your intention, was to create an array of length 5. So, is it worth it? That saves you, a little tiny bit of typing, I guess, and makes the code a little bit harder to understand. But technically, you don't need to actually even specify how large the array is if you are initializing it. Because it can figure out, oh, there's 5 things. You wanted an array of length 5. If you are then specifying the length, again, a value of 5 here, you actually don't need to initialize any or all of the elements. So you can choose not to initialize it at all when you declare it, just like for other variables. You can also choose to partially initialize it as well. So for this circumstance where it is of length 5, but we're only providing 2 values to initialize it with, as part of the spec, it would initialize the other elements in that array to 0. That's one of those issues that Replit kind of papers over a little bit for us, but having arrays not being appropriately initialized is a very common programming mistake that you'll be running into. One way to guarantee it, if you're worried about it, you can always just specify, here's my array, initialize one element to 0. It'll initialize all the other elements to 0 as well. That kind of gives you full array initialization without having to write any code for doing that. So that is static allocation and potential initialization of arrays. I'm required, I think, to tell you that C does support variable length arrays relatively recently, and with varying level of supports from compiler to compiler and system to system. So depending on what compiler you're using, what system you're on, it does allow you, and this is a relatively recent change, to declare my array of n, where n is an integer that's defined in your code. There are all sorts of reasons why we do not want to do that, but first and foremost is it is something that's allowed for sort of optional support. And if you try it, your code may work today and it may not work tomorrow. And depending on the value of n, it may work until you change n and then it no longer works. So technically this can be done. And you may see some code examples, although as a relatively new feature, not as many code examples as for more traditional ways of doing this. But for this class and the restricted kind of academic environment we are in, we're not going to be doing that. If you kind of want that type of feature for now, where you can change how big that array is going to be, my recommendation is to use this kind of approach, which is a compile time determination still. If I want to change length from 5 to 15 or 150, I have to recompile my program, but it's still relatively dynamic in that hopefully I'm just changing one thing in my program and the rest of the code kind of follows, and we don't have to overthink changing the size of that array. In some sense, that's all we need to know about arrays. Now, just we need to get some experience with how we use them, how it kind of connects to the other things we have already been doing this semester. Let's take a look at the memory view of what's happening. And it's really not that different than our existing view of memory, right? We declare a variable in our program, and we know that it's going to eventually be placed somewhere in memory by the compiler as well as the underlying operating system that your program is running in. We knew that for the existing types, an int was going to be 4 bytes, and a float was also 4 bytes, but 4 bytes kind of stored slightly differently. A double was 8 bytes and things like that. Our memory view of arrays is effectively that, except for instead of having just one value associated with the variable name, there is going to consequently be an array of such values associated with that variable name. They are not guaranteed to increment in a positive direction sequentially, but by and large, that's what all systems tend to do, all compilers tend to do. So in my code, I have declared double resistors of size 100. The variable name is going to be called resistors. It's going to be 100 doubles. And so consequently, the amount of memory that's going to get allocated is going to be 800 bytes. Each double is 8 bytes. And if you ever are not sure about that, you can look back to lab 1 or the examples we did. There's that built-in size of operator that returns how many bytes are associated either with a variable name or a type. That would return 8 on all systems. There's 100 of those 8-byte doubles. In total, there would then be 800 bytes associated with that variable name resistors, and their relative locations would be given as kind of illustrated in that little graph up there, where resistors of 0 would be the very first value. Then resistors of 1, all the way up to the very last value would be resistors of 99. Why do we tend to write our for loops? For I equals 0, I less than n, I plus plus. It's for the same exact reason, because we are usually writing our for loops to be working with arrays, and in C, our arrays start at index 0, with relative offset from the starting location of 0 bytes. So in some sense, that's a very powerful thing, right? If I wanted to allocate 800 bytes using just regular variable names, I'd have to be allocating all sorts of different variable names, and the code would become very unwieldy. Resistor 1, resistor 2, up through resistor 100. You could do it, but it's pretty limiting, right? Whereas if I decide I need 100 resistor values in my program, that's just one line of code, and it allocates all 800 of those bytes, all 100 of those doubles. And then later I go through and realize, oh, actually 100 wasn't enough. I actually need 100,000 resistors in my program. Now that's not feasible by naming your resistor 1, resistor 2, resistor 3, but changing this should be very trivial. make it 100,000, and then now you have 100,000 of those resistor values, those variables in your program. So hopefully you can see, at least without even worrying about what type of problems we solve with arrays, that in terms of the memory allocation capability it gives us in our C programs, it's a pretty powerful thing. One variable name, roughly the same amount of code as declaring any other variable, right? Little brackets, that's about it. And more memory in theory than any system you could ever execute on if you give it a big enough value inside that bracket. So in C, this is kind of directly flowing from this view of what's happening. And all I can do is just kind of say it and say it multiple times, and then you just have to experience it. In C, like several other programming languages, but unlike also several other programming languages, if you have an array of length n, the valid subscript values are integers in the range 0 to n minus 1. If you try to pass a float to your subscript, it will not work. If you try to pass -1, unlike other programming languages, it will not work. If you try to pass something greater than n minus 1, it may or may not do what you hope it would do. Many other programming languages uses ranges that count and start at 1. Others allow even more flexibility than that. In C, our flexibility comes from that what goes within that subscript, what goes within that square brackets, can really be anything. It can be a constant, it can be a variable, it can be expression, it can be the return of a function value. It could be itself the value of an array being subscripted. As long as the end result of whatever is within the brackets is an integer, it will compile. And as long as whatever's within that subscript, once it's fully evaluated, is within that range 0 to n minus 1, you'll get some value being read from memory corresponding to that array. So this is example array fun. Let's take a look at it in Replit. I mentioned that Replit, again, papers over some of these memory allocation bugs that one may experience. Int y is an array, and it's initialized to 7, 3, 2, 1, 5. So what's the size of that array? 5. Again, it is not at all a bug or a flaw to do that, to be very explicit and say, this is of size 5, and I'm initializing it to 5 values. Again, and on the flip side, you could also say 50, and it would initialize the other 45 values to 0. Sure. If the number is short, yeah, I don't know. That should be an error, because it wouldn't have anything to do with it, and I do see excess elements in array initializer. Again, that's one of those compiler messages that is quite correct, but then you have to kind of translate it from compiler to human understandable English. Excess elements in an array initializer, yeah. You declared this array of size 3 and you tried to shove 5 things in there. There are excess elements in the thing we're using to initialize. That's the code analyzer that's just kind of running in the background. Does it compile? I'm guessing no. It did compile. Let's ignore the fact that it compiled. It did weird stuff though, right? Well, because we're checking values that don't exist. So let's stick with the value of 5 to just illustrate that. There's kind of your answer. It did compile. We initialize it to 7, 3, 2, 1, 5. We also have a separate variable I. Again, in C, I'll just say it again. If you have an array of length n, the valid subscript values are integers in the range 0 to n minus 1. So you have to kind of phrase it a little awkwardly when you say it out loud. The first value is at index 0, always. Or 0 is the first. However you want to phrase that, we start at 0 for our arrays. Just write that down, remember that, and you're in better shape than most C programmers. We start at 0. Consequently, there's a little bit of cognitive dissonance that when I say print out y of 2, I think that's still how I would phrase that, y of 2, but that is going to be the third entry in the array, right? That's the consequence of starting at 0. 0 is the first, 1 is the second, consequently 2 is the third element in that array. So when I print that out, what value is it going to print out for line 6? It's going to print out 2. because this would be y of 0, y of 1, y of 2. It's not that common. We want constant indices into our arrays because we're usually writing programs to access these arrays, and so we would have variables associated with it. So y of I is also perfectly valid, where I is initialized to 3. That would print out 1. How about y of I plus plus? It's also going to be 1, right? We talked about, and I mentioned not to sweat it too much, prefix versus postfix increment, where you have plus plus I versus I plus plus. I plus plus takes and uses the current value of I, and only when it's done doing that, then it does the plus plus. So I is still 3 when it gets access in that array. Whereas if I were to then do it again, the value of I would be 4 after that I plus plus. Then it would actually print out 0, 1, 2, 3. Then it would finally print out a 5. So there should be 1, 1, 5, 5 in that example then. Likewise, if instead of I plus plus, I did plus plus I, that's our prefix increment, where increment I first, then use it. That would give us 2, 1, 5, 0. 2, 1, 5, 5, 0. Anything is fair game for our subscript. Anything that evaluates to an integer will compile. Anything that evaluates to an integer in the valid range will give us a value from that array. So we oftentimes, and this example is synthetic, but you will be writing code that is absolutely going to be array of an array of an array. If you have more than 3, that's usually a sign something's gone wrong in your thought process, but still you will have that in your code starting this week, if not this week, starting next week. So while this looks kind of synthetic and meant to trick you, it's not that far off. You just have to work inside out. So figure out what needs to go in my final subscript. To do that, I have to go look at the subscripts that are within that, and if there's more, we go kind of inside and our way back out. So we have to evaluate y of 1 plus 1. Y of 1 is what? Y of 1 would be 3. Yeah, we got it, because that would be y of 0 would be 7. Y of 1 is 3. We then literally just add 1 to that to get 4. That gives us y of 4, which is why it is printing out 5. But unlike other programming languages, and I think I'd say all modern programming languages, C as a language, outside of certain compiler flags that by default are not necessarily even turned down, does absolutely nothing for that last circumstance here. My memes are dated, I'm aware. I'm willing to take recommendations to kind of update this for maybe next semester it's not so embarrassing for everyone involved. Y of I plus 2. It evaluates to an integer, compiler's happy. You'll notice there's no compiler warnings, no squiggly lines, and it's not like it's because it's close or something like that. Y of I plus, don't want to poke it too much, but y of I plus 2 million. Nothing from the compiler's perspective is wrong with that. But from our logical programmer's perspective, that seems very bad. Even going back to y of I plus 2. The value of I, and I changed it to plus plus I, but it doesn't really matter. The value of I is 4 at this point in the program when you've gotten to line 10. Started as 3, we have incremented it. It is 4 after that fact. So y of I plus 2 would be y of 4 plus 2, or y of 6. What is y of 6? Well, that's 0, 1, 2, 3, 4. There is no 5, there is no 6. What that returns is very system dependent. In this case, Replit as a educational software environment for those who are looking to prototype quickly and learn is content to return back out a 0 for that value. There's no requirement in the C specification that it return back 0 for that. Anything is fair game, as is crashing your program and returning an error and just returning back to the operating system saying failed. We can't access that location in memory. What ultimately then just happens, And we don't have quite the same picture here to kind of show it here, but we could do the equivalent for this resistors array, is that subscript logic, when it finally gets compiled down, is really ultimately just calculating an address. That when I say resistors of 2, what ultimately gets compiled to is an assembly instruction that says, give me the base address, the location in memory where we started resistors, and add because it's 2, add 16 bytes to that base address. And that's all it's doing. Give me the starting location. I said it was going to bleed into pointers. This is going to be part of the pointers discussion. Give me the base pointer. Give me the starting location for where that array is defined in memory. And then calculate how many bytes from that starting location I need to be. Because it's 2 for resistors of 2, that is 0, 1, 2 doubles off from the starting location. So 0, 8, 16 bytes from the starting location. Consequently, what does that code do for y of 6? Nothing magical. Give me the starting location of y, and I don't even know where it is. We can print it out if we really wanted to know. It's at some location in memory, and calculate 6 integers off from that starting location. Or 2004 integers off from my starting location. So what will it print off when you do y of I plus 2000? Whatever happens to be in memory at that location. And if your process, your application has access to that memory, it'll print out whatever it happens to have. If you don't have valid access to that location in memory, it should rightly crash. To me, it's a problem that this does not crash, y of I plus 2000. Maybe Replit just provided a lot of memory to me. We can actually analyze how much memory it's using. I have been given, I don't even know what that means, 36 plus 48 divided by 2 gigs of memory here is what's been provided. I would need to make this very large indeed to go beyond that. Let's give it a try. I mean, we should at least try to crash things every so often. That's, am I missing one? That's 4 million integers. How many bytes is 4 million integers? Each of them are 4 bytes each. 16 megabytes, 16 million bytes. That's not nearly enough. 4 billion integers, though. Now we're talking 16 gigabytes, right? So given, I haven't tried this. I don't know what it's going to do. Give me the base address of y, and then now in that printf whatever is 16 gigabytes further along in the address space. And unless you pay more, there's a limit to how much Replit should provide you. Let's see what happens. Still a 0. I don't see how that's possible. Maybe that's somebody else's memory, or maybe it's smart enough to determine that it shouldn't be able to access that. You're out of a range. Yeah, you should be able to crash it though. That's going forward in memory. Let's go backwards in memory. Still getting it to 0. Oh, we should absolutely be able to crash this given a little bit more thought. I'm very disappointed. Well, you know, that's a lot of digits now. That's a very large address that it's calculating here. We can crash it. Y of I plus 2. I mean, we can crash it. We can definitely crash it. Y of I minus the address of I minus 4 times I. Cannot, invalid operands to, because y of I minus, it's really unhappy about that. Minus where y is starting. It's very unhappy with that. Invalid operands to binary expression. That's the name of it. Invalid operands to binary and int of 5. I want to get the address of it. That should not be calculated. We're just trying to do bad things to crash the program, not have a compiler error. Thankfully we We finally got it to crash. That was me being naughty. What am I doing here? I'm saying, give me y of I, but minus the location of the start of y itself, and then minus the number of bytes corresponding to I. So give me x has location 0 in memory, and that should crash pretty much any system. If your code starts to look like that, it's bad news. I'm going to delete that so we pretended we didn't actually see it. Major takeaway, we allocate our array, and we're doing so statically. N, you can call it n for all your arrays for now if you'd like to. 0 to n minus 1 is our valid index. It's not always so clean. And again, as we saw, I think most circumstances this is a bug, right? I mean, we're just printing out a value, but still, it's outside the valid range of our array. And the compiler, the code linter, the analyzer did nothing to prevent us from doing that. It returned to 0. Sometimes the 0 is okay, and so you don't even care or notice that you printed out an extra 0. But generally, that's a bug. You don't, if you're printing out values in an array, you don't want to print out things that aren't actually inside your array. And unlike other programming languages, in C, you don't get any real helpful hints that you've done that. The trick really is to kind of go line by line and inspect your code and determine, are the things I'm putting inside my subscripts in between my square brackets here, are they valid? It's not always that straightforward. This is what makes it not a trivial topic to cover in that sense. If I'm not sure if this is good or not, I should probably print this part out first and then confirm, yeah, it's within my range. That's the main mechanism we have for debugging our variables. There's now an extra layer of kind of debugging because now we have to debug our subscripts as well as the actual values of those variables. It connects very well, this concept, to the topic of for loops. You could argue that for loops are created to be able to deal with and work with arrays more than anything else. If after declaration we had an array called Z that we wanted to initialize to a set of values of 0, 1, 4, 9, 16, and 25, after declaration, that syntax where we specify those values in curly brackets is not allowed. You can do that at declaration time, but not after you've done that declaration. After you've declared the array and you'd like to set values of that array, you have to do it one by one. You have to individually subscript and update those values. So one method in terms of what code we'd have to write to initialize and set those values of Z would be to kind of line by line go through and do it. So you have 0, 0, Z of 1 is 1, Z of 2 is 4, etc. In this case, if we recognize some geometric or algorithmic or other pattern associated with it, then the for loop is going to be a very natural fit for working with our arrays, for reading and updating values of our arrays. In this case, what do we recognize about our subscript? If the subscript is 0, the value is 0. If it's 1, it's 1. If it's 2, it's 4. If we have then a for loop, for I equals 0, I less than 6, I plus plus, we could initialize Z of I to just I squared, or I times I here, to get the same exact result. For maybe 6 values, it's not worth it, but if it was 600 values, it would definitely be worth it to write the program, to write the loop to do that versus kind of manually encoding those values. These are what your loops are going to tend to look like. Again, you have to kind of keep track of that start at 0, that n minus 1 kind of issue, but to not confuse yourself any, this is an array of length 6, right? The valid indices are between 0 and 5. There's 6 things. So our for loops generally, unless you're doing something kind of, really specific with that array, our for loops for working with that array of length 6 are going to be I equals 0, I less than 6, I plus plus. Because what are the values of I when we do that loop? It's 0 through 5, right? When I becomes 6, we exit the loop. So we never access Z of 6 in that loop, right? You could also have done I equals 0, I less than or equal to 5, I plus plus, that's the same exact for loop. I think it's more common to, again, define your length somewhere in your code, your n value, where n is 6 in this instance, and then do I equals 0, I less than n, I plus plus. I have a problem solving. Oh, great. We have a question. Sure. Thought you were going to ask me about my favorite peanut butter brand first. For for loops, it doesn't really matter. You mean like, do I do plus plus I or I plus plus right here? This is kind of a standalone statement that gets executed at the end of every iteration of your loop. So in terms of its impact, doesn't make any difference at all. The only difference that happens when we have pre versus post is if we're doing the plus plus in addition to something else on that same line of code, where we're both incrementing as well as using the variable at the same time. In the for loop, it doesn't matter. I've seen some people who, I don't know if it's idiosyncrasies or what, who do plus plus i's in the for loop, but I'd say this is the textbook example of how to write a for loop that iterates 6 times and does 0 through 5. Let's leave things right here for now. We'll do some problem solving exercises on Friday. Please come back on Friday, otherwise I'll miss you.